Thank you, Denis. Thank you, Michelle, for the kind invitation. So I'm going to give a talk on a few subjects related to this, how to use dissipation as a resource. So we know that usually dissipation gives rise to decoherence and is bad for quantum states. But we'll see that it is also possible to use it as a resource to stabilize some states of interest and to do even something more interesting like quantum error correction. So that's a subject we've been following, we've been working on for a few years now, in particular in collaboration with the team of Michel Devereux at Yale. Here, well, I'm gonna try to talk about 4 particular proposals. 2 of them have given rise already to experiments, and 2 of them are just at the level of theory proposals. So I don't know whether I'll be able to cover all of them, but we'll try to see. So the joint work on the theory side has been this has been a joint work on the theory side with all these people. So who have been previous or current students and who have left, and some of them, like Zaki's, are already a colleague. And then at Yale, some students, Yuri Wu and Curtis Gerlings, and postdoc Shyam Shankar and Michel himself. So, okay, first of all, let's start with this. So we saw this figure this morning at Michel's talk. So, what is state stabilization? What is stabilization? What is the difference of stabilization and preparation of a quantum state, first of all? So when we talk about stabilizing a state, usually we are not only interested in preparing, we are really actually more interested in robustly preparing, which means that even if we have some uncertainties, we want to be near the state that we want to reach. And more than that, we want to protect it against decoherence, against various noise channels, and keep the system at that particular state. So that's what's the difference between the stabilization and preparation of a quantum state. And so essentially, we need to evacuate some kind of entropy from our system to be able to stabilize the system around a particular state, or eventually a manifold of quantum states. So in case of quantum correction, we're not interested in stabilizing a single state, but a manifold of quantum states, for example, 2-dimensional manifold of states, which would be the logical qubit in a quantum computer, in a quantum processor. So this is the experiment you saw this morning in Michel Devereux's talk, so which was one of the first experiment where actually quantum feedback was able to stabilize the photon number state of this cavity. And so in principle, the way this was done was just by measuring these Rydberg atoms, as you saw this morning, one by one, and based on that to estimate the state of the cavity and decide what to do with the cavity, essentially decide about the phase and amplitude of a coherent field, which will be injected in the cavity and to stabilize a photon number state, a particular photon number state. So that's nice. Here I'm going to rather focus on superconducting qubits, and there are some thing which is going to harm us if we want to do a similar thing with superconducting qubits. There has been some feedback experiments, measurement-based feedback schemes with proposals with. Okay. So here, the first thing to note is that with these superconducting circuits, we deal with systems which have coherence times which are much shorter than what we saw this morning. So, for example, we saw that we have this for this cavity, we had a lifetime of the photon of about 130 milliseconds. For superconducting qubits, typically we have, at the best, for the best superconducting qubits today, we have a lifetime of about 100 microseconds. So it's about 1,000 times faster dynamics. Well, that might be somehow saying that, well, we're never going to have a chance to do anything. But in practice, it appears that it's actually, we can do pretty much everything, but in a different manner. Because the thing is that, well, even though the system is much, the coherence system is much shorter, we have much stronger couplings and much stronger nonlinearities as well. So essentially, it is possible to still operate on the system in a coherent manner during the lifetime of the system. The only problem is that the interface with the classical world is hard, because in the classical world we cannot go, we are going to be limited by electronics. And so we are not necessarily able to do calculations as fast as we need. And so that's somehow the idea of using this what we call dissipation engineering is that, well, in these kind of systems where we have short coherence times but high nonlinearities or strong nonlinearities, strong couplings, well, it is possible to do something like an analog feedback circuit and to control the quantum system by remaining in the quantum world, but never getting out of the quantum world, essentially never trying to interface it with a classical computer and do calculations in real time to guess what we need to correct on the system. And so essentially the fact that we have the capability of designing Hamiltonians with these artificial atoms superconducting qubits is also going to be very helpful for these kind of processes where we try to control the systems by remaining in the quantum world. And the next thing is also that we have, well, this is something which is also, in the case of Rydberg atoms, is useful. You're dealing with microwave signals instead of optical signals, and these are well controlled with commercial electronics. And so that's nice as well. Okay, so that's what we try to do. Essentially, what's dissipation engineering? So this is a system, a system that is of interest for us. We want to stabilize it in a state or in a manifold of quantum states. And so what we want to do is that we want to engineer some kind of interaction between this system and another quantum system, which I call a reservoir. And so what essentially we can do is to engineer the interaction Hamiltonian between these two systems. And we want to use the dissipation of this reservoir to stabilize our system around a particular state or a manifold of states. That's what we want to do. And so, in principle, we have, this is a high Q system. This is a very coherent system. This is a very low Q system, essentially. We want to have a large separation of time scales, and we want to use the dissipation of this system to control the other one. So, okay, the way we would model this mathematical terms is that we have this interaction Hamiltonian as Hamiltonian of the system, Hamiltonian of the reservoir, and the interaction Hamiltonian. And then we have this dissipation, but we can assume for now that it's just a dissipation on the dissipation channel on the reservoir, by assuming that the dissipation of the system itself is weak enough. And so the stabilization goal is to stabilize the system around a particular coherent state, pure state of the system tensors whatever on the reservoir. So we don't care what the reservoir ends up with. We just need to know that the system itself, the system ends up in a pure state. So in a projector on a particular pure state. So that's what we want to do. Essentially, we want to engineer this. So I'm going to give you 4 examples. So the first one, which is a very simple, we can consider it as an optical pumping experiment, is just cooling a qubit. We have a superconducting qubit. We want to stabilize the ground state, whatever state you start from. We want to stabilize. So, well, of course, if you wait enough because of the T1 decay of dissipation or natural dissipation of the qubit, you know that you will end up eventually in the ground state. We want just to make it faster. And we want also to remove some of the spurious thermal excitation in the qubits that is usually relevant for the case of superconducting qubits. We always have some, superconducting qubits are usually a little bit hot, and we want to cool them down to have a higher population of the ground state. So that's the first thing I'm going to talk about. We're going to see that the same ideas could be used to autonomously stabilize a Bell state of 2 qubits coupled to a cavity. Next, I'm going to talk about the case where we have 2 qubits in 2 separate cavities, and we want to entangle them, to stabilize entanglement between them. I'm going to explain how we might use these kind of ideas to stabilize remote entanglement. And finally, I'm going to talk about autonomous quantum error correction if I have time. Okay, so here is the idea. So it's essentially the opposite, the reverse experiment from what Michel told us about this morning. So we have a qubit sitting inside a cavity, and these are the photons of the cavity reading out the qubit. So essentially, the idea is that we're not going to read out what's going on. We're not going to look at what's going on. We're just going to use this dissipation along with some drives on the qubit to stabilize the ground state of the qubit. So this is what it looks like at the experimental level. So we have, this is a harmonic, what plays the role of a cavity is an LC oscillator, this particular experiment, which was done in 2013 or 12, I think. And so we have a transmon qubit, an artificial atom, sitting here in green, which where we have adjacent junctions here, as you see. And so this system, the way to model it, as I mentioned earlier, is that we have the Hamiltonian of the qubit, which is essentially a qubit, the frequency of the qubit, and some drive on the qubit at given uq of t. So that's the drive. That's what models this red arrow here, which is essentially the drive on the qubit. We have the cavity Hamiltonian, which is the cavity's frequency omega c, and some drive on the cavity, which is at resonance. We can assume that it's at resonance, or we can choose its frequency. We're gonna see it later. So that's essentially the drive coming inside the cavity. And then I'm gonna always assume this kind of dispersive coupling between the qubits and cavities. So that's all over through the talk. We're gonna just have this kind of interaction between qubits and cavities. So that's what we saw also this morning. This is the kind of, so essentially the cavity's frequency is being shifted as a function of the qubit excitation, and vice versa, the qubit's frequency is also shifted as a function of number of photons inside the cavity. So that's essentially this Hamiltonian that Michel told us we can use for measuring photon number inside the cavity. So you also see this a similar picture to this in this morning. So this is what we call the strong dispersive regime of interaction between the qubit and cavities. So essentially, the thing is that if you do a spectroscopy of the cavity, you might see, so this is a regime where this dispersive coupling chi is much larger than the line width of the cavity and the qubit. Both qubit, so 1 over T2 is the line width of the qubit, and kappa is the line width of the cavity. So in this regime, if you do a spectroscopy, so this is what Michel called like dress state spectrum this morning. Essentially what you see is that if you're going to have two frequencies well separated for the cavity based on whether the qubit is in ground or excited, and the same thing for the qubit, for the qubit, you're going to see many peaks. Essentially here you have a Poissonian distribution as we have a coherent state inside the cavity, but you have many peaks. So the first one corresponding to the cavity being in zero photon number state, 1 photon number state, 2 photon number state, and etc. So we have all these peaks that are well resolved, and we can address them separately. Okay, so the idea is all through the talk is just to use this kind of strong dispersive regime to do various things. That's I'm going to try to explain. So I'm going to start by this. So let's assume that we can have this qubit coupled to this cavity, and we're going to drive the qubit, the cavity at its frequency omega r is. It means just that we're going to conditionally drive the cavity, condition on qubit being in the excited state. We can also drive the qubit conditionally on the cavity being in photon number state n bar. Okay, so these are, we can choose essentially, this means just that we choose this UQ, the frequency of or UQ or UC are going to be given by these two frequencies here. Then what would happen? So let's assume that you have, so we can show everything in this diagram, through this diagram. So essentially you have the qubit being in ground and cavity being in 0, 1, 2, etc. Or cavity being, qubit being excited and cavity in the state 0, 1, etc. And we have vacuum state inside the cavity, but the qubit could be in any state. So it could be in a thermal state, but it could be also in a coherent superposition of ground and excited. And what we want to do is essentially to stabilize everything in ground and 0. So this is the simpler things. So we want to rapidly make this population converge toward ground and 0. So that's what we want to do. We call it cooling the qubit, essentially. So the idea is that so here is the two spectrums that I showed you earlier. So the cavity spectrum based on the qubit state, and the qubit spectrum based on the cavity cavity for the number excitation. I'm going to turn on this drive on the cavity, as I mentioned, as I showed earlier. What it's going to do is that if the qubit is in excited state, it's going to drive my cavity to a coherent state. Essentially, if you turn on a drive on the cavity at its resonance, it's going to put a coherent state inside the cavity. But here, as I'm choosing the frequency to be this one, it means just that it's going to put a coherent state only if the qubit is excited. If you're in ground, nothing is going to happen because you're off resonant. Okay. So essentially, you end up with this kind of coherent state around n. Then I'm going to turn on this particular transition. As I mentioned earlier, this corresponds to this particular peak of the cavity, of the qubit. And so what's going to go on is just that you're going to make a hole in your coherent state, essentially. You're going to have, what's going to happen is just that some of this population is going to start to oscillate between excited and ground state. And then, because of the decay of the cavity, because in this manifold we don't see any drive, the cavity is just going to naturally decay to its vacuum state. So essentially you have a kind of a pumping which brings the population there and then pumps back, brings it back to the ground state. So you eventually end up with putting all the population in the ground state. So in practice, what you do is just that you turn on these two drives at the same time. You don't have to do anything else. You just choose two drives at well-chosen frequencies. We don't need to do anything with their phases or amplitudes. You just turn them on, and it's going to cool down continuously the qubit to its ground state. Okay. So it's nice because most of the other cooling schemes is work by putting the two systems at resonance. Here we don't need to put the two systems at resonance. They remain apart in frequencies. We just turn on some drives and we orient the entropy in a way that at the end we end up with a state that we are interested in. We could have done the same thing in an opposite manner. So we could have done this drive and the same one here, and we could have stabilized the excited state instead of the ground. Okay, so that's there is nothing that. So if you just instead of this blue curve, you use this one. Instead of this peak, you had used this peak, you would have stabilized actually the excited state. Okay, so this is fully symmetric because you would have brought this there, then there, and then because of dissipation, you would have ended up in the excited state. So this was done in experimentally in 2013. So you see it here. So essentially, it allows us to reduce the reset time of a superconducting qubit. In this particular case, the superconducting qubit's lifetime was 37 microseconds. So if you wanted to do nothing and just try to wait for it to get to the ground state, we should have waited a time of order 37 microseconds. No, we have reduced it to 33 microseconds. So we have a high Q system, but whenever we want to restart it, we can do it very fast in 3 microseconds. And this essentially, this 3 microsecond is set by this decay rate kappa, essentially, because those other drives, we can choose them as we wish. So essentially, this rate, how strong this dissipation is going to give us how fast can we reset things. And so something other that you can see is that if you look at these dashed curves, this is essentially when this is the excited state population when you start from because the qubit here was still a little bit hot, so it had about 10% thermal population in the excited state. So what we see is that just by turning on these drives, we actually cool it down in a temperature which is much lower. So essentially, the ground state population at the end is the excited state population at the end is much smaller. So this is the excited state population, and over the time, we start, if we don't do anything, essentially, this dashed curve corresponds to the case where there is no, essentially, initial preparation. We just have a qubit in its thermal state. So it has 10% population in the excited state. We just turn on these two drives, and we cool it down to this state, which is the excited state population, which is much smaller. Okay? So in this sense, we can call it a cooling procedure. Okay, so that's nice. Now we can show that exactly the same thing could be used to stabilize more fancy states, like an entangled state of 2 qubits. So the idea is that we have now 2 qubits, Alice and Bob, sitting inside a cavity, inside the same harmonic oscillator. And the idea is that we want to drive them with some continuous drives. Again, similar to the other situation. We want just to apply some continuous wave drives, CW drives, but we want to choose their frequency in a way that the steady state of this whole system is the Bell state for the qubits and whatever for the cavity. Okay, so we want to have a Bell state of the two qubits. So here is the idea. We're going to use, first of all, some kind of symmetry. We're going to try to make these qubits interact with the cavity in a way that the chi's, the two dispersive couplings that I mentioned in this kind of, so we have this dispersive coupling between between Alice and the cavity and Bob and cavity. We want to make these chi-a's to be the same or similar. Essentially, we want to make them, the difference between them smaller than kappa of the cavity. That's what we want to make. So what it means is just that when you look at the cavity spectrum, the two peaks corresponding to qubit to Alice being in excited and Bob in ground, or vice versa, they overlap pretty much. Okay, they are very near to each other. We don't care about excited, and ground. So we have three peaks now for the cavity based on whether the two qubits are ground, two qubits are excited, or they have odd parity. In the case where the odd parity. The qubit spectrum as well has all these peaks. So the qubit Alice and Bobcat could be at very different frequencies. You don't need them to be at the same frequency. So here, for example, Bob is at a higher frequency and Alice is at a lower frequency, but Bob is going to be, Bob's frequency is going to be shifted as a function of number of photons inside the cavity. And the same thing for Alice. And always, as this chi-A equals to chi-B, the shifts are similar in both cases. So this is the first ingredient. So we need to make this symmetry. So we can engineer it in the experiment, essentially. And the next thing that we're going to use is just that if we apply the drives somehow in the cavity, we can apply it on the qubits. So if we start to drive these qubits, we can drive them in a way that some of these Bell states are dark states. So for example, if we have a drive on qubit Alice and a drive on qubit Bob, if these drives have the same phase, we are actually applying a Hamiltonian of the form sigma, same phase and amplitude. We are actually applying some Hamiltonian of the form sigma xa plus sigma xp. In that case, what we can show is that this drive would not affect this Bell state, so the excited ground minus ground excited, whereas the other phase would be affected. So essentially, for this drive would not drive the one particular Bell state at some particular phase. And if you change the phase here between the two, so if you make them the phase between them pi, then you would actually have the other Bell state with a plus sign, which becomes an invariant state. Okay, so that's the second idea that we're going to use, the second ingredient that we're going to use. Then this is the whole protocol, what the whole protocol looks like. So we have, again, this kind of diagrammatic scheme. You have the qubits. So we have 4 possible states for the qubits, ground, ground, excited, excited. I'm going to use now the other bases, phi plus and phi minus for the qubits. So phi plus being the Bell state with the plus sign, and phi minus being the state Bell state with the minus sign. This is the state we want to stabilize. We want to stabilize phi minus, for example. And the cavity's excitation is also encoded in 0 to n, as you see here. The idea is that we start by applying 2 drives, which are at the cavity's frequency when both qubits are excited or both qubits in ground. So these are these 2 peaks. I'm going to start to drive them. What we're going to do is that we're going to put the population in ground, ground, and excited, excited in a coherent state of the cavity. Okay. Now I'm going to put a drive on the qubits Alice and Bob, which are going to be selective on cavity being in 0 photon number state. So we know there are all these peaks. So we're going to only drive the qubits if they are in this manifold and not there. Okay. But we're going to choose the free phase of these drives. So we're going to lock the phase of these drives such that this phi minus state remains an invariant state. That's what I mentioned here. So I'm going to apply this drive, so the phase of them are locked, so that this Bell state is a dark state. It's not touched by the drives. So this could be shown by this diagram. So essentially, phi plus goes to some superposition of ground and ground and excited, which are then driven to these coherent states. So this essentially, what it does is just that the population which is in phi plus is also going to be shelved in these two states, essentially. Next, I'm going to put two other drives on the qubits, now being selective on cavity being in n photons. So these two other drives. And I'm going to choose the phase of them to be opposite, so that essentially the qubits know this phi plus is the dark state, and phi minus is driven to excited, and ground. And then I just wait, because of the dissipation in this manifold, I don't see any drive, and I just end up in phi minus 0. So we have a hope here. We have a pumping scheme which brings any population in these states to phi minus. If you wait enough and you have a T1 jump, so that this phi minus, for example, jumps to GG, then these drives would bring it back to phi minus, to correct it. If you have a T2 jump, so phase jump, phi plus would jump to phi plus, which would bring both back to ground, excited, then pump there, and then dissipate back to phi minus. So this is by just turning on 6 drives. So the idea here is just that we're going to have these 6 drives always on. These two drives, Alice 0 and Bob 0, they need to be locked at some phase, and Bob and Alice n should be locked at the phase which is pi shifted with respect to that phase. So that's what you need. So we have, and then you turn them all together, and what you see is that you're going to stabilize and you're going to keep a Bell state inside your cavity. So this was experimentally done in 2013 as well at Yale. And so we see that we could get a fidelity of the Bell state of about 80%. And we keep it there, this fidelity. So essentially, if you come back after 500 microseconds, whereas this lifetime is something about 20 microseconds, I think, for these qubits, you still have the same fidelity of the Bell state inside the cavity. OK. Now I'm going to try to show how this could be further extended to the situation where the two qubits, so the two qubits are not at the same place. So here we have the two qubits inside the same cavity. So so somehow it's some kind of easy entanglement, I would say, because they are sharing a degree of freedom, and it's easier to entangle such a thing, such two systems, than if they are separate and they are not interacting directly together. But here, they don't really interact directly together. They interact with a common degree of freedom, which is the cavity degree of freedom. But we want to do something more complicated. So we consider that we have two cavities, and two qubits in them. OK? And each of them coupled in the same manner, still in the strong dispersive regime, as I mentioned earlier. And we want to know how can we entangle stabilize an entanglement between two qubits, which are at distance. The idea is that, well, we need to share some kind of quantum correlation between them to be able to do that. Otherwise, you could also use, of course, some kind of measurement-based entanglement scheme, like what is used in quantum communication protocols. But here we want to stabilize things, and so this is. I don't know any method except sending some correlated drive on the two systems, so that we can apply such kind of entanglement. The idea is that we're going to use one device which is called the three-wave mixer, which essentially produces two-mode squeeze states. Okay, so essentially it's we send a pump at frequency omega 1 plus omega 2, omega 1 and omega 2 being the frequency of the two cavities. And we send inside the cavities, instead of sending coherent states inside the cavities, we send two-mode squeeze states in the two cavities, at resonance with the cavities, not the qubits. So have to be careful. And the qubits now are driven themselves with some local drives, with some regular Rabi drives that, as we had before. So we assume that we have some Rabi drives on the qubits and some correlated drives on the cavity with this two-mode squeeze state. How could this be modeled? Well, first of all, the interaction, if we don't assume these local drives, the interaction between the qubits and cavities could be reformulated in this form. This, of course, the initial thing, as I said, the initial form, it could be formulated in this manner: chi1 sigma z1 tensor A dagger A plus chi2 sigma z2 B dagger B. Okay, so, but this could be reformed. We are going to assume chi is to be the same. So this is going to be the same chi. And this whole thing can be written as chi sum of sigma z1 tensor sum of A dagger A plus B dagger B plus chi. Well, there is maybe a factor of 2 here. This could be written in this manner. There is the figure. Okay, this could be written in the same, this formulation. So this is what I show here. What I call n is actually this sum of A dagger A and B dagger B, and what I call m is the difference between A dagger A and B dagger B. And what sigma z1 plus sigma z2 is sigma gg minus sigma ee with this notations, and sigma z1 minus sigma z2 is this sigma minus plus, so what essentially brings the Bell state from minus state, from phi minus to phi plus, or vice versa. Okay, so this is essentially the interaction, Hamiltonian. The fact that we have correlated drives on the cavities could be modeled by this correlated dissipation channel of the two cavities. So essentially, the cavities are going to be dissipating now, not with the operator A and B, but with this Limblad operator, A cosine hyperbolic of R. Well, R is essentially the squeezing parameter in your two given set by how what's the gain of your essentially squeezer, two-mode squeezer, plus A2 dagger sine hyperbolic of R. So this is essentially using the Gardner's formalism of cascaded quantum systems. You can do these calculations. You can show that if you apply, instead of applying vacuum state on a cavity, you apply a squeezed vacuum on a cavity. You change the dissipation channel from A to these kind of operators. So that's what we show. Okay? So you have two dissipation channels because you have two cavities, but with this kind of correlation between them. Now the idea could be catched here. We have still the same kind of situation. If the qubits are in ground, both in ground or both in excited, then we're going to deal with this part of our dispersive Hamiltonian. So because we are in this manifold, the other manifold is going to give 0 because sigma minus plus is 0 for these two. So you see, when I have green here, corresponds to this green part. So this part of Hamiltonian becomes 0 when we are in ground or excited, both in ground or both in excited. And if we are in the odd parity manifold, then this is the part of the manifold, the part of the Hamiltonian which would act on my system. The thing is that what you can show is that presence of this Hamiltonian and this dissipation, the steady state of the cavity would be a two-mode squeezed vacuum. Whereas in presence of this other Hamiltonian and cavity dissipation, the steady state would be a two-mode squeezed thermal state. So these are two different states. So essentially, you have a thermal state, which is squeezed in one situation, and the other one is a vacuum state, which is squeezed. So we have, again, the separation of the two manifolds in the cavities. Now, if you turn on the two local drives that I had mentioned earlier on the qubits, you do essentially the same thing. You choose the phase to be well-chosen, to be locked, such that the ground excited is driven to phi plus, but phi minus is remain untouched. Next, when we are in the two-mode squeezed thermal state, we have also coupling, because of our Hamiltonian, between phi minus and phi plus. Why is that? Because this term of Hamiltonian becomes non-zero if you're in a thermal squeeze state, whereas it becomes 0 when you are in a vacuum squeeze state. Because in a vacuum squeeze state, the number of photons in mode A and mode B are the same. So this operator M, which I had defined here, which was the difference of photon numbers, is 0 when you are in this manifold, but is non-zero when you are in this manifold. So because of this M being non-zero, you essentially have a coupling between minus and plus, or vice versa, whereas here you don't have any coupling between the two. So what happens is that now you have a complete graph. You see whatever state you start with, you're going to end up with phi minus and 2-mode squeezed vacuum in the cavities. So you essentially drive whatever, if you start from ground, you go there, and then you come back here. If you start from phi plus, you go there, there, and there. If you start from phi minus and some thermal state, you also have this coupling which evacuates entropy. And you start from excited as well. So whatever state you start with, you can see that this is the only state which could be stabilized, again, inside the two cavities. Well, these are some numericals here. We don't have any experiment yet. So it seems like this protocol is nice, but it's not very robust to some noise, dissipations, some imperfections. I'm going to talk to you about them. So what you see is that what's nice is just that even with the slightest squeezing, you can get 100% Bell state. Even if you have just 0.1 dB of squeezing, if you wait enough, you're going to end up with a perfectly Bell state, perfect state. So this is the green curve here, but you need to wait a lot of time. So this is the time in kappa minus 1. What you see is that if you increase the squeezing, you increase the rate of convergence towards the Bell state. But even with the slight squeezing, you get 100% Bell state. So in this sense, we call it accumulation of entanglement.
For all these processes to work, you have to control the dissipation process.
You have to, what?
You have to be sure which dissipative processes play a role.
Well, here...
So you select one which does what you want.
Well, usually we have...
But you may have different kind of processes, dissipative processes.
Yeah, we try to bring, as you see everywhere here, we try to bring it down to the natural decay of a cavity harmonic oscillator. So essentially, this dissipation channel that's mentioned here, it boils down. It's just a harmonic oscillator, regular harmonic oscillator with its regular decay channel driven by a squeeze state. That's and so we believe that this is actually that for a harmonic oscillator is by far the major decay channel of harmonic oscillator. All the other two decay channels are not. Well, we see that this is nice, but we need to, if we want to start with the small squeezing, then we need to wait for a kind of long time. No, the bad news is that this is quite fragile with respect to the transmission efficiencies. If you have this in your transmission lines in this scheme, if these transmission lines are lossy, which is unfortunately the case, we're gonna lose a lot of this final entanglement that we can reach. What can be shown, for example, here is in these three curves is that this is the perfect efficiency. You have perfect efficiency. With any squeezing parameter, you can get 100% concurrence of the qubits. So that's in perfect situation, of course. I'm assuming perfect qubits driven. That's what we show here in this curve as well. As I mentioned, with any amount of squeezing, you can get to 100% in theory entanglement. But as soon as you bring this eta to 90%, then you see that you can never go beyond 50% of concurrence between the two qubits. And this, what is nice though is that we know that we can, this protocol is more robust if we have a smaller squeezing. So in that sense, if you start with a smaller squeezing, you're more robust to transmission loss. Yes?
So it's not equivalent to start with a very weakly squeezed state, or to start from a strongly squeezed state and to have losses?
No, this is not equivalent. In this situation, it's not equivalent. So if you had that, if you had situations where you had this squeeze state acting on the qubits, so at frequency of the qubits, then it would have been perhaps the same thing. No, it's as we are driving it to the cavities with squeeze states, in that sense, it's different from because there has been protocols where people proposed to derive with squeeze states 2 qubits. So Cross and Sirac had some proposal around this 2004. But those, I don't think they have the same properties. Here we are essentially preparing a quantum correlated environment for the qubits. And in that sense, we have some more robustness if we start from a small squeezing. We could see it as some kind of distillation as well, I'd say. I mean, so it's maybe not, it could be somehow maybe explained by some entanglement distillation proposals as well. Well, there is no measurement involved here, but okay. Anyway, so what we see is that it is nice to start with to work with small squeezings, but at the same time to be more robust. But at the same time, we lose in the rate of convergence. So at 1 dB, for example, which was the case of that you see here. At 1 dB, you have this blue curve here. So essentially, the time is about 100 times longer than kappa of the cavity. Essentially, it means just that if you want to make this whole thing work, you need to have qubits which are very well separated in lifetime with respect to this kappa, maybe 4 or 5 orders of magnitude separated from the cavity's dissipation. So this seems to be hard. So we are working still on seeing if there is a way to make this more robust by some changes in the scheme. Okay, and so maybe just to finish, we could also use these same ideas to do autonomous quantum error correction. Yes?
Before you switch to the subject, I have not understood this 100% fidelity. If the 2T1...
No. I'm saying that, of course, no. I'm saying that if you have perfect qubits, that's what I was saying. So if you have perfect qubits, small squeezing, which is not, because one would say that a small squeezing is far from ideal entanglement, but you can accumulate that to a Bell state in principle if you have perfect qubits. Of course, when you don't have perfect qubits, you're going to lose. That's why. Yes.
In the previous experiment, you showed that the reservoir engineering doesn't care about the qubit.
Yeah. Here neither, but it cares in the fact that if you remember here, you get to 80%. So it means just that this 20% is because of the T1 and T2. So essentially, what happens is just that you have this time of convergence towards the phi minus, which is given by kappa, and then you have the time the T1 jump times, the times that it takes. So the time scale at which you get out of that state, and you have a competition between the two of them. So you want this to make this correction time to be much faster than this T1 and T2 jump times. Exactly. That gives you that 80% or. It's exactly this ratio between the two. Yeah. It would be exactly the same thing there. So that's why I mentioned here that if you want this to make work, you need to be somewhere where this convergence rate is not so slow, so that when compared to this T1, T2 time of the qubits, you get still a good fidelity of entanglement state, of entanglement. That's what. Sure.
Why is eta so like 0.9 for eta sounds low?
Well, no, actually, I think in experiments we have never been able to reach this number. 90% of transmission has been quite hard. In principle, there are many reasons for this to be lossy, this transmission lines to be lossy. In particular, these elements that we put here, a circulator here, is usually a lossy element, for example, in these kind of circuits. Of course, you can try to do engineering and make things better. You can try to make these circulators out of superconducting material, and I think then you might win a little bit in these losses. But practice, I think I've never seen an experiment where they have been above 80% transmission. So it's quite challenging. It's pretty much as challenging as making good qubits to make good transmission channels. So in order to just explain what is the idea for autonomous quantum error correction, I'm going to explain this on the case of a simple quantum error correcting code, the bit flip code, where we have 3 qubits, and we want to protect these 3 qubits, the states of these 3 qubits, against bit flips. So essentially, 0 becoming 1 and y becoming 0. No phase flips. We don't assume any phase flips. We assume that these 3 qubits are coupled to a cavity, again, as similar to before. And we are in this dispersive coupling regime, and we're still in this strong dispersive coupling regime. We have also these other terms. I'm not going to comment about them. This is because the qubits nonlinearity induce some nonlinearity on the cavity, but you don't need to take care of the to look at this. Essentially, you can just look at the first part, which is the part we have seen before. What we want to do is to protect any state of this form without knowing what is C0 and C1. So we will start from a superposition of 0, 0, 0 and 1, 1, 1, and we want to protect them against bit flips. So we assume a few things. We assume that we are in the strong dispersive regime as before. So the chi is larger than kappas, than the decay rates. That's similar to before. And we assume some kind of symmetry. We assume that the sum of chi's is equal to is 0 or small to respect to kappa. Well, of course, in superconducting qubits, it's hard to change the sign of chi's. What you could do is just instead of using this encoding, you could use 0, 0, 1 and 1, 1, 0 as encoding, and then this condition would be chi plus chi 1 plus chi 2 minus chi 3 equals less than 2 kappa. So you can make these symmetries even in case of superconducting qubits. So that's not a problem. Okay, but I'm going to assume that we have this such condition. So the sum of chi's is very small, while the absolute value of each of them is very large. And this is going to be the diagram that we could explain everything. This is a diagram in the rotating frame of the qubits. So essentially, it's the frequency of the cavity. If the qubits are in the manifold 0, 0, 0 and 1, 1, 1, because of the symmetry that I mentioned, the sum of chi is equal to 0. Essentially, the cavity has the same frequency. So the frequency of the transition between 0 and 1 of the cavity is the same whether you are in 0, 0, 0 or 1, 1, 1. Whereas it's different if you are in 1, 0, 0 or if you are in 0, 1, 1. The idea is now that you could assume that you have a dissipation channel, a bit flip channel, which brings this 0, 0, 0 to 0, 0, 1, and at the same time 1, 1, 1 to 0, 1, 1. Now, if you have a drive which somehow could drive this state to this state and this state to this state, then because of the dissipation of the cavity, you would have actually correction of the qubit state. The interesting thing is that this blue curve is at a different frequency than the red curve, even though in this figure they appeared in the same frequency. This is as it's in the rotating frame of the qubits, they occur different frequencies. So this corresponds to the qubit 1's frequency. This depends on yeah, I'm going to show that later. But so these two drives are not the same. So we have two different drives here. And the other thing is that this red curve could not drive the 0, 0, 0 state out of the 0, 0, 0 state because it's off resonant here. And the same thing for the blue one there. So essentially, whenever you are in this state, you are dark to these drives. You don't see them, and you remain there. Whenever you get out to these bad states, you're corrected towards 0, 0 and 1, 1. So this corrects only the first qubit, of course. We are not correcting the second qubit yet. Of course, one could say that in order to correct the other qubits, we could have three cavities coupled to these 3 qubits, and then add the corresponding drives for the other cavities and correct the whole thing. In practice, you can do it easier. I'm going to explain that in a bit. So essentially, the Hamiltonian we want to engineer to have this scheme that I mentioned here is this. So the cavity is being coupled to the qubits with these chi's, with a symmetry condition that I mentioned earlier. And the qubit needs to be coupled to the cavity in this manner. So essentially, the cavity absorbs a photon by putting an excitation in qubit 1. And this becomes only resonant if the sum of these chi's is equal to 0. If this part of Hamiltonian is equal to 0, otherwise this is off resonant, because this omega is going to be assumed to be much smaller than chi's. So this whole thing becomes off resonant if this is not 0. And so this is the condition that I was mentioning here. So essentially, this becomes off resonant when you're here and not when you're here. This is the selectivity. So you need these assumptions. You need to make this chi to be much larger than kappa, which is itself larger than omega, this coupling rate between the two. And how can we make these omegas, such kind of interaction between the two qubits when they are not at resonance, between cavity and qubit when they are not at the resonance? The idea is that you can apply pumps. So this is parametric methods. By applying some pumps, which are at some given frequencies, omega A minus omega B1 and omega A plus omega B1 divided by 2, you can actually engineer some such kind of interaction between the cavity and qubits. So essentially, we're going to have 4 drives. Here we're going to have 2 drives, and to correct, we need 2 drives at these 2 frequencies to correct for the first qubit. And in order to make now this scheme to correct any of the 3 qubits, we need to add 2 more drives. Perhaps I'm not going to explain that. Essentially, these 2 more drives are essentially bringing the errors always on the first qubit. So if the error happens on the second qubit, they bring them to the first qubit, and then this is corrected with this scheme. And the same thing for the third one. Oh, okay, so this is some numerical simulations. It is hard, but what it shows is just essentially that with some parameters like this, which are maybe achievable, which is like, let's say, the decay time of the cavity of order of a few kilohertz, and the decay time of the cavity of, this is the qubit and this is the cavity, of order of a few hundred kilohertz, and some chi coupling of order of tens of megahertz. So you see here, this is the matching condition, 15 plus 15 minus 30 becomes 0. So that's what matching condition, the symmetric condition that I mentioned earlier. And some Rabi drives that I have chosen here, some drives that I mentioned here. What you get is this. So if you have no correction, you have this decay of the system. And if you start to correct, then you see that you improve this lifetime by some order of magnitude. And so you can actually calculate the effective decay rate, which is going to be given by some ratio of the omega squared divided by kappa. So essentially, as omega is smaller than kappa, is smaller than kappa. Again, kappa is going to set what is the rate at which you can correct things. Okay, so there we have some ideas also on how to do full conomer correction with these systems. So not just correct for bit flips. This is more involved. And so there is this. This could be. You can see the PhD thesis of Joachim Cohen, defended like in January this year on that. So I'm gonna finish here. So what I would like to say is just that it seems like this. We can do a lot of things with these only using CW drives and these systems involving superconducting qubits and cavities. We need strong dispersive couplings between qubits and cavities. These are the resources we have used in all these proposals. Strong dispersive couplings between qubits and cavities. Separation of time scales between high Q and low Q systems. Some amount of symmetry. So this is essentially this separation of time scales between high Q and low Q systems could be achieved by using Purcell filters. We need to have strong couplings, and we need to have strong separation of time scales. In order to do that, we need something like a Purcell filter usually. In particular, in the second experiment I talked to you about, we had a Purcell filter to make that happen. To this stabilization of Bell state was working because of this Purcell filters. We need some amount of symmetry usually, and we try to put these symmetries on the things that we can engineer easier, more easily, like the dispersive shifts. Not the frequencies, for example, which are harder to make exactly the same for the qubits, the superconducting qubits. And we can use these parametric methods, as I mentioned at the end. So this is the 4 essential ingredients that are used in these schemes. And it seems like we can do much more with these 4 ingredients, which are all provided by these superconducting sequences. So, okay. Well, yes. So usually these simulations, all the simulations I showed you are in the higher level system. They are not on the effective system. So they are in the real system with all the imperfections. So usually if you look in these papers, we try to explain all the second order effects because of all the effective the approximations in the second order. So yes, so that could be as small as if you make this. So these higher order terms are because of these separations that I mentioned here. So chi, essentially kappa divided by chi, and this divided by kappa are going to be the epsilon in your second approximation. So essentially, if you can make them smaller and smaller, you're going to get better and better results, of course. But yes, so that's.
It wasn't quite clear to me how much is calculation and how many experiments there are.
So the first two proposals have been experimented. The two last proposals are only proposals at this level. Of course, for the bit flip error correction, it's not going to be useful because the real decay channels are not bit flips. So we cannot use this. That last one is an idea of how to go towards corner correction. But at this level, we're using only bit flip correction. You can not do anything experimentally because there is nothing. You can do something with phase flip error correction if you were connecting bit phase flips, because you have phase flip decay channel as a single decay channel, but bit flips never appear separately from phase flips, essentially. Yes.
How would you change the phase of chi in the time?
So that's with transmit qubits is rather hard to change the sign of chi. Usually that's why I said in all the three first proposal we don't need to change the sign. We just need the chi to be the same. For the last proposal we need this sum to be equal to zero. But as I mentioned, you could change this by being the sum of the two minus the third one equal to 0 by changing the encoding from 0, 0, 0, 1, 1, 1 to 0, 0, 1 and 1, 0, 0, 0. So your logical 0 is going to be 0, 0, 1, and your logical 1 is going to be 1, 1, 0. So
If you actually want to change the phase of chi, then
yeah, it's more engineering. Essentially, what happened in the transmit case, you need to make the harmonicity of a transmit larger than the detuning between the transmit and the cavity somehow. So you need, if you want to remain in the dispersive regime, and it's kind of hard. So essentially, you need to have a much smaller coupling. It's hard to make large chi's and change the sign as well. That's somehow. You need to go in a very particular regime, which is called the straddling regime, where you can change the sign of chi, and it's somehow very narrow region of parameters where it happens. Yes.
We mentioned the two epsilon that was a problem, but does the effect also
Depends on it depends on which one we're talking about. So in this particular case, no, because we are always only dealing with the single Fock state 1. We don't really. The other ones, I don't think neither. I think most of them we have. I don't know about this one. I don't think it's really detrimental. It might be. I have to check, because in this case it might be a little bit detrimental, because it might lead to this two-mode squeeze vacuum being not to meet two-mode squeeze vacuum, and then you're going to have some coupling between phi minus and phi plus, and that's bad. So that might be harmful for this situation. I don't think for the other two situations it's going to be harmful. Because on the two other situations, we're going to work with just coherent states. This is really squeeze states are fragile states. So yeah, this is the only protocol I would say it might be harmful. Yes.
What we discussed a little bit, the remote entanglement accumulation. So you said that small squeezing is more robust. It takes a longer time. So what is the price to pay in practice for this longer time in a realistic experiment?
Well, that's, as I mentioned, it's essentially you're going to have the final fidelity is going to be given by two things. So this is, first of all, this is the final concurrence. So if you put eta equal to 1 and you fix the squeezing parameter here, 3, for example, this is going to be the maximum if you put eta equal to 0.9. This is going to be the maximum concurrence you can get. You cannot go beyond that. That's for sure. Okay. So I say that you can get, let's say, 40% concurrence. That's for sure. You cannot go beyond that. Now, you need also to make sure that this 40% is compatible with the time of the convergence because, well, we choose this curve, 1 dB, so this is the one. So this time is about 100, the time that it takes for convergence is about 100 divided by kappa. So if this needs to be much shorter than T1 and T2 of the qubits, essentially. If essentially the ratio between these two is also going to set you the maximum concurrence you can get. So this, if this ratio is, let's say, times T2 is, let's say, of order of, I don't know, 10%, this means just that you cannot get beyond, let's say, something like 90% fidelity of your Bell state. So your concurrence is going to be limited. So this is essentially, you have a compromise of the two. You can calculate, and we haven't done it, but we can give a region essentially with this particular T1 and T2 and with this particular eta, what is the best efficiency we can get. But it seems to me that today, with what I see from these two curves, it seems to me that you need qubits which are beyond 100 microseconds T2 to be able to get to see, let's say, a 20% concurrence or something like that. If you have a transmission efficiency of 90% or 80%, so which is quite challenging. So it seems like this is very hard at this level to be applied. So this is what we want to improve, essentially. Yes. Yes. No, any superposition. Any superposition against bit flips. So if we assume that there is nothing else than bit flips, we stabilize any superposition. Because what happens is just that because of this indistinguishability between 0, 0, and 1, 1, we never induce in this protocol any kind of dephasing between the two. So essentially, we start from any superposition of these two. A jump would bring us to a superposition of 1, 0, 0 and 0, 1, 1. And this is going to be corrected by these two drives without any knowledge of whether we are there or there, essentially. This is going to become coherently, bring it back.
The sum of your key is not exactly 0, you don't accumulate some phase.
Yeah, if you have, essentially, that's true. So that's this ratio between the two. So that's what I was saying. This epsilon here, so the ratio between these two is it gives rise to some, so this is going to be this squared divided by kappa is going to be some effective dephasing rate between the two. So that's what is this second order, one of these second order terms that plays a role here is that it's going to be that.
You said you're not fully protected because you cannot protect against phase errors.
That's true. That's here in the protocol.
All you have to do is go to a different basis. Why can't you just
Yeah, so that's true. Yeah. No, they're totally. So we have actually, it is hard to go to a different basis. That's not easy because here we are using chi's. So we are using a transmit qubit, the energy levels of a transmit qubit, and for this in this basis we have this Hamiltonian that I showed you, that's an Hamiltonian. If you change the basis, you need to change it actively somehow. You need to apply some drives to change the basis to the X basis or from the Z basis. Well, yeah, of course. If you can engineer a different Hamiltonian, that's nice. So, but that's the question is how to engineer a different Hamiltonian. So, yes, but we have some idea on how to do that. So in this PhD test that I mentioned, we have also a section on explaining that we can, in principle, do the phase flip error correction. It's going to be a bit harder than the bit flip because you need to engineer it effectively by applying some other drives.